So, welcome back to the problem solving session on this course, Introduction to Abstract and Linear Algebra. My name is Harshita. I'm a PhD student at IIT Tirupati. So, today we'll discuss some questions related to the content of week 7. Yeah. So, we'll start with this question. So, it says, what is the column rank of a certain matrix? So, I would like to mention a small point, like correction compared to what I said last time. So, what were we trying to do? We were trying to convert it into a certain form and then just count the number of non-zero rows or columns, right? So, there's a small subtle point which I missed last time, which we'll correct this time. So, what is column rank? You look at the columns of this matrix. So, you have 2, 3, 1, 1, 2, 1, 4, 6, 2, 3, 9, 6. So these are all some vectors in R3, right? So these vectors span some subspace of R3. So if you look at the span of this, it will be some subspace. So we'll just call it something so that I don't have to write it again. So span of V1, V2, V3, V4. This is some subspace of R3. And the dimension of this subspace, call it W. So dimension of this subspace W is what is called the column rank. Right? So definitely, since it's a subspace of R3, the rank will be less than or equal to 3. Now similarly, if you look at the rows, each of the rows is a vector in R4. So you look at the space formed by those vectors. Whatever is the subspace that it generates, you look at the dimension of that. That is called the row rank. So we call W prime is the span of the rows. 2, 1, 4, 3, 3, 2, 6, 9, 1, 1, 2, 6. Right? This is a subspace of R4, and whatever is its dimension, that is called the row rank. So in both case, you look at it. Since this is a subspace of R3, the dimension will be less than or equal to 3. And here, since it is the span of 3 vectors, this will also be less than or equal to 3. And it is a fact, can be proved, that given any matrix, the row rank is always equal to the column rank, which we just generally call as rank of a matrix, right? And probably you would have seen another definition of the rank of a matrix, which is the smallest R such that there is an R cross R minor which is non-zero. So you can look at the lecture notes. So that is also an equivalent definition of all these three numbers are actually turn out to be the same. So if you have to find the column rank of this matrix, you can either find the row rank or column rank. Let's try to do any one of them. Let's just do the column itself. So what we'll do is we'll convert it into a certain form. So what we'll do is we'll reduce the matrix So when we reduce, we mean by applying column operations. So that two things hold. First thing is all 0 columns are to the right, and second thing is a leading entry in any of the columns. So leading entry comes below or down of leading entry in the previous columns. So when we solve an example, it will become a little more clear. Yeah, when we say leading entry, we mean non-zero entry, just to clarify. That's what is a leading entry. Okay, so let us take the matrix in hand. 2, 1, 4, 3, and we'll reduce it to this form. So 2, 1, 4, 3, 3, 2, 6, 9, 1, 6. Okay, so what we'll do is take the second column, subtract the first column, C2, we'll do C2 minus C1, so this becomes 2, 3, 1. So next step, I'll just do two operations together. So C3, we'll do C3 minus 2 times C1. So what I'm trying to do is get these entries 0. Also, we'll do C4 minus 6C1, 3, 1 minus 1 minus 1, 0. This becomes 0. Now we'll just subtract 9 times C2 from C4. So C4 get 2, 3, 1. And finally, since we want the leading entry to be below, this is also fine actually. If you look at it from down, the non-zero entry is coming in steps. But since I've written it the other way, we'll just do C2 plus half C1. this one. Okay, so now it is in the form that we have. Now we just count the number of non-zero columns. That will give you the column rank. So column rank is 2. You try to do the same thing with row operations and get the row rank. Even that will turn out to be 2. Any questions?
Is there any other? Hello, ma'am.
Yeah, yeah.
Is there any other method to find out the rank, column rank,
Mm,
without operating this lengthy process? Shortcut method.
yeah, that's why I said since column rank equal to row rank, you can actually just do the row operations also. But without doing any of the operations, I'm not sure.
I mean,
Yeah,
determinant,
you can
determinant
determinant
can
when
you use determinant of, as in the case of square matrix or m cross n matrix, while calculating rank,
yeah.
we use determinant.
Yeah, so determinant you can use it, but I think it will be more tedious. See, when you say determinant, you have to find out the smallest R cross R matrix which gives non-zero determinant,
Yeah.
right? Sorry, largest R cross R matrix which gives non-zero determinant. So you can, like, then you'll have to calculate a lot of determinants, right? You take all the possible 3 cross 3 matrix, which itself is like there are 4 possibilities. And if you get all 4 of them determinants as 0, then you take all possible 2 cross 2 matrices, which will be a large number of possibilities, right? So that will probably be more tedious task. Like if you look at this matrix itself, so if you want to calculate all possible 3 cross 3 minus, what do you have? We have this matrix,
Hmm.
we have this matrix, then you
Yeah.
take these 3 columns and so on. So you can do that, but
Rank, maybe rank of matrix and column rank, is it same?
yeah, yeah. Rank of a matrix, column rank, row rank, all 3 quantities will turn out to be the same number.
It is same. No, that is okay.
Yeah, yeah. Any more questions? So here, see, the rank is 2, which means you take all 3 cross 3 matrices, the determinant is supposed to be
Zero.
0.
Zero. Yes.
So you can actually check computing the determinant of all the 3. You'll have 1, 2, 3, 4, 4 3 cross 3 matrices that come out of this. It will be 0. Any more questions? Okay. We'll move on to the next question. Let A be a matrix of order 4 cross 4 and 2, minus 3, 0, 5 be the eigenvalues of A. Then the determinant of A is equal to. So, does somebody want to say what are the eigenvalues? What are all the things that you know about eigenvalues? What is an eigenvalue?
Root of the characteristic equation
Mm-hmm.
zero. It is the root of the characteristic equation of matrix.
Yeah. So value is one way. One thing is it is the root of the characteristic polynomial. There Okay. Polynomial. This means so lambda is an eigenvalue of A if and only if determinant of A minus lambda I equal to 0. Okay. Second is so lambda is an eigenvalue of A if and only if there is a non-zero vector non-zero. So if A is n cross n, B is a non-zero vector in Rn such that AB will be lambda times B. So you take the vector V, you multiply it with A, it will just be a rescaling of the vector. So one thing, 2 points to remember, if you get all the eigenvalues, there are two relations which you get, which is basically sum of eigenvalues. So this is equal to trace of the matrix and product of eigenvalues will be determinant. So yeah,
It is 0.
exactly.
Determinant
So
is
here, since 0 is one of the eigenvalue, so the product will be 0 and hence the determinant will be 0. So this also leads us to one observation that if 0 is an eigenvalue of A, it means the determinant of A is 0, which is same as saying that the matrix A is not invertible.
matrix is
So
not inverted.
0 is an eigenvalue of A if and only if the matrix is not invertible.
It is singular matrix.
Ma'am, means A inverse does not exist.
So let's move on. Okay. So we have a matrix A uh, and you have four equations that is satisfied by A. Hello. You have four equations satisfied by A and you want to see which of these equations holds true for the matrix A. So what do you think these equations are?
What is to be found out?
You have to find out which of these is satisfied by A.
Okay, okay.
See,
So
one thing is you
you have to
can
find out
substitute
first.
the value of A.
You have to find out first characteristic polynomial of A.
Yeah, exactly. So Cayley-Hamilton theorem says that Hamilton theorem says that if you have a matrix and you find out its characteristic polynomial, the matrix satisfies its characteristic polynomial. So you substitute in the characteristic polynomial, you get 0. So a matrix, roughly saying, satisfies its Screen resolution is quite low. Oh, okay. Maybe I'll. Is it okay now for
Madam,
others?
the screen is not displayed. Yes, it is okay.
Yeah, yeah. I just stopped sharing and
Yeah,
started
okay, okay.
sharing.
Yeah.
Yeah. So it satisfies its characteristic polynomial. So here we'll just find out what is the characteristic polynomial. So how do you compute the characteristic polynomial? We compute determinant of either xi minus a or a minus xi. Doesn't matter. So this is what we'll want to compute. So this is determinant of x minus 1, 1, 0, minus 1, x minus 2, 1, minus 3, x plus 2. And this is just computing the determinant. So this will be x minus 1 into, so this into this minus this into this. Yeah, did someone say something? So x minus 2 into x plus 2 minus of 1 into minus 2, which is minus 2, then minus 1 into uh, this, so minus of x plus 2 minus of minus 3, which is x minus 1 into x square minus 4 plus 2 minus x.
And x cube minus x square minus x plus 1.
Sorry?
I mean the final value, ma'am. X cube minus x square minus x plus 1.
Yeah, x square minus x square minus x plus 1. That will be the answer. You can just finish it. Minus 2. So you can compute it, it will turn out to be this. So since this is the characteristic polynomial, the matrix satisfies this polynomial, which means a cube minus a square minus a plus identity matrix will actually be equal to 0. So, this is okay? Okay.
Ma'am, this characteristics polynomial will be always xi minus a in the form.
You're talking about this one?
Matlab this polynomial will be always in this form.
In this form as in, yeah, this is how you compute the characteristic polynomial. Characteristic polynomial is nothing but the determinant of xi minus a.
Okay, ma'am.
A minus xi.
Sorry?
It can be a minus xi.
A minus xi, that is also fine. You will get the negative of this.
Yeah.
Or maybe it depends on the order of a. Yeah, it will depend on the order of it. So you'll either get this or the negative of this. But it's okay. When you're trying to find the roots of the polynomial, it won't really matter. Yeah. So, sorry? Yeah.
You can find out
So,
this characteristic polynomial by any other method.
uh, no, this is the only way. I mean, see, another method as in, it's like you go backwards. If you are given the eigenvalues, you can write out the characteristic polynomial. Right? Like you go back to this question. Okay, let's go back to here. So here you don't know what the polynomial, you don't know what the matrix is. But can you tell me what is the characteristic polynomial? Just by looking at the data that we are given.
I don't get you.
Okay, see, in this question, what is it that we have? We have that there is a matrix A of order 4 cross 4 and these are its eigenvalues. 2, minus 3, 0, 5 are its eigenvalues. The question is, instead of determinant is equal to something, what if the question is what is the characteristic polynomial of A?
Okay.
So how would you answer this?
A minus 2i or a plus 3i. A.
Exactly. So what is it that you know? The characteristic polynomial, the roots of the characteristic polynomial gives you the eigenvalues, right? So you are given the roots. How do you get the polynomial? So you know that it's a 4 cross 4 polynomial,
It is
and you know that its roots are given by 2 minus 3, sorry.
x minus 2 into x plus 3
Exactly.
into x minus 5
Exactly. So
into x into x.
the characteristic the polynomial will be x minus 2 into
X plus 3
x plus 3 into x
x
minus 0 into x minus 5.
x minus 5.
Yeah. Okay. Okay. So let me ask another question aside. So let's say A is a 5 cross 5 matrix and its eigenvalues are, so the only eigenvalues that it has is, write it that way, the only eigenvalues of A are plus and minus 1. So can you tell what is the characteristic polynomial?
X plus 1 x minus 1. Sorry, 5 by 5, no? So it is a
Mm-hmm.
x plus 1 raised to 5, x minus 1, x plus 1.
Yeah, anybody wants to comment?
5 plus 5 by
Okay,
5.
can you actually get the characteristic polynomial with just this much information?
Actually, the sum of diagonals should be the eigenvalue, right?
Sum of diagonals should be
The eigenvalue means
It is a 5 matrix means there must be 5 eigen.
it's a plus or minus 1 means then it should be quadratic.
It must be
then it
x plus
should be
1 raised to q into x minus 1 raised to 2. Yeah.
Hmm. X plus
Yeah,
1
okay.
or X minus 1.
X plus 1. There must be 5 eigenvalues, no? For 5 cross 5 matrix.
So, right. So, you are only given that all the eigenvalues are plus and minus 1, but you don't know how. We have not given you the see to get the characteristic polynomial explicitly. It's a 5-degree polynomial,
It's a 5 degree,
and
yes.
as you said, you need to have 5 roots. So when we say these are all the eigenvalues, all we are saying is that these roots are appearing with some multiplicity, and how many times each of these roots is appearing we have not mentioned, right?
Yeah, these three
So
are,
in fact,
it can be other. Means there is
so it can be any of the possibilities. So you
any of possibilities. Yes.
guess exactly what is the characteristic polynomial, but you can say that the characteristic polynomial has to be one of these. X
Oh,
plus 1
okay.
cube, x,
Hmm.
Yes.
sorry. So,
Yeah, yeah.
yeah, that's it. So these are the only 4 possible characteristic polynomials.
Hmm.
Now,
You are
additionally,
discussing
some other information.
you are discussing week 8 or week 7?
Uh, week 7.
Okay.
Yeah.
I'm sorry, I joined late. That's right.
Oh, okay. No issues. So these are the possible characteristic polynomials, and maybe some other additional information. Suppose you know additionally that the determinant is, let's say, if additionally um, you know that determinant of A is 1, then what can you remove any of these possibilities, or all the 4 characteristics polynomials possible? Is the question clear?
Determinant of
What
A.
I'm saying,
Yes.
in addition to the information given in the question, we are saying that determinant of A is 1. So then
It's
can
a
you,
square matrix. It's a square matrix. Okay, anyway, you have also given 5 by 5.
hmm,
What is the relation determinant and
so determinant, as we already saw this, determinant is the product of eigenvalues. That is one
okay.
of the questions.
So,
Yeah.
so it can be either 1 or minus 1.
Uh,
No.
no, see, you just look at the possibilities. Look at the first one. What are the eigenvalues here? So you have minus 1 occurring 4 times.
So square root is fine. Square means to the power of 4 is 1. So that will work.
Exactly. So this multiplicity of minus 1, when I say multiplicity,
Hmm.
this power that comes, it has to be even, right? Because you want the product to be
Awesome.
plus 1. So if in addition this information is given, you will have lesser possible number of characteristic polynomials. So 1 is possible. You can just check the others. So 1 and probably 3.
1 and 3.
Yeah.
And one thing, x plus 1 whole to the power of 4. So that means that eigenvalue is
Minus 1.
how you
So
wrote
minus
minus 1? What is the elementary step what you did to get minus 1?
x plus 1 power 4 into x minus 1. What are the roots? Minus 1 is occurring 4 times, right? And 1 once. If you have this polynomial, what are the roots of these polynomials?
How you found the roots? How you
Which
found the
root?
roots? The x plus 1 whole to the power of 4 and x minus 1. How you found for x plus 1 it is minus 1? What is the elementary thing? What
This is,
and
oh,
x minus
okay.
1
So,
it is 1.
yeah, yeah. So this is what we used to do in school. This is equal to
That's
0,
what.
right? What does root mean? That this is 0. So since the
Okay, okay.
product,
Now x plus 1 whole to the power of 4 is 0 or x minus 1 whole to the power of 0.
yeah, or
Yeah,
x
yeah, yeah.
minus 1.
Okay.
Right? So, no, the point of this question is that you may not explicitly, just by looking at it, say what is a characteristic polynomial, but the small information that you have, it may help and help you to go closer to the polynomial. That's it. Maybe if trace is given or some other information given, it will be easier to find out. Yeah, any questions? Okay, and maybe one more point that I would like to add related to this question that we just now did. So, we saw that A satisfies this equation, right? So, what are all the ways that you know to find the inverse of a matrix? How do you, so let's take the same matrix that we had. So what are all the possible, like what are all the methods that you know to find the inverse of a matrix?
First, the matrix should be invertible, no?
Yeah. Let's take an invertible matrix, this matrix itself. You assume that it is invertible for now, and then I'll come to the point as to why it's invertible. Sorry?
Nothing, madam. You can continue.
Okay. Two minus 2. Okay. So in class, I think sir has done two methods, one already. So one is you assume it is invertible. So you say that A inverse is adjoint of A by determinant of A, right? And the second one, if we have time, we'll compute it. So the second one is you use elementary transformation to reduce this to identity matrix, and then you look at what transformations you've used. So we'll just come back to that if we have time. So I'll just for now write using elementary operations. Okay. So apart from these two, just looking at this, can you tell what is the inverse of the matrix? We have computed the characteristic polynomial, and we have got that the matrix A satisfies the characteristic polynomial. So, can any of you say if we can find the inverse of the matrix from here? Just look at it and see. Yeah.
Can similar question is there in the graded assignment, but I know that it is not supposed to be discussed. How to approach question 3 means after you just
Which question, sir?
question number 3, week 7. Okay, you please complete this. After that, we can take it.
Okay.
But
Okay. See.
but it is
Yeah.
related to some.
Okay. Yeah. We can discuss after this. So, anybody wants to say something? You just look at the equation that we have. See if we can see what is the inverse. it is A, when multiplied with some other matrix, you have to get the identity.
Then A transpose, huh?
A inverse equal to minus A square minus A plus identity.
Yeah. How did you do that?
We can put the elements other than I to the left hand side, sorry, right hand side. So then we
Yeah,
can multiply A inverse by both sides.
exactly. So, see, once you have the characteristic polynomial, you know that the matrix satisfies this, right? So, we just have this. Now, you take uh, just the identity matrix on one side. So, let's minus a cube plus a square plus a equal to identity, right? From this equation, all we have done is taken identity to the other side, or the other three terms to the other side. Now you look at it. Here you can take a common. So you can write it as a times minus a square plus a plus identity equal to identity. So what have we got in doing this process? We have got a times some matrix B equal to identity. And what is
Okay.
the inverse of matrix? It's exactly that matrix which you multiply with A to get identity, right? So this B is nothing but,
Ma'am, please repeat, ma'am, this last two step.
okay, just a second. See, we had this characteristic polynomial and we know that A satisfies the characteristic polynomial, right? So
Yes, ma'am.
you know that A satisfies this equation. Now, what we've done is, in this equation, just taken all these three terms to the right hand side, or taken identity to that side. So what is it that we have? A cube minus a square minus a plus identity equal to 0. So I've just taken all these three terms to this side. Right? Should I write it the other way? It's just which side of the equality you hold. So 0 equal to a cube minus a square minus a plus I. So these three terms, you take it to the other side. So we get minus a cube plus a square plus a equal to identity matrix, right? Now in left hand side, you can take a common outside, right? So when you take a common out, what we get is a into some other matrix, whatever is remaining in the bracket, equal to identity. Now, what is the inverse of A? Inverse of A is precisely that matrix which when you multiply with A gives you the identity, right? What do you mean by A inverse? It is some matrix which satisfies this equation. So that is precisely what we have got here, right?
So B is A inverse. B equals to A
Yeah. So
inverse.
B has to be A inverse. So let's go back and see what allowed us to do this. What allowed us to do this is we have an identity matrix here, sitting here. Or in other words, what we are saying is when we have the characteristic polynomial, if we have a constant term, where is this identity coming from? This constant term of the characteristic polynomial, right? This constant term is what is giving you the identity here. So in the characteristic polynomial, if you have a constant term, it means the matrix is invertible. So this is another way of seeing that the matrix is invertible. So what I'm saying is, if characteristic polynomial of A has a constant term, then A is invertible. when I say constant term, it is understood that it is non-zero constant, right? So let us actually correlate this to what we saw before. See, what did we see? This is just, I'm sorry, it's a small digression, but it's like interesting things. See, what did we see? A is invertible if and only if determinant is non-zero, and determinant is product of eigenvalues, right? So let me just put all the strings
We are
together.
covering week 7,
So
right?
A is
We are covering week 7
yeah.
syllabus,
So
right?
constant. Sorry.
We are covering week 7 syllabus, right?
Yes. 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 Is something is something wrong?
No. I just want to know which week we are
Okay.
actually.
Yes. Yes. Wait. So this is not there in the questions, but I just wanted to add it. So A is invertible if and only if determinant of A is non-zero. Right? And we already saw that determinant of A is product of eigenvalues. So what are eigenvalues? Eigenvalues are nothing but roots of characteristic polynomial. So now do you see the connection? When is the constant term? Okay, if you remember your school algebra, whatever, if you have a polynomial, so the constant term is basically the product of the roots of the polynomial, right? So if you have some polynomial p of x, the constant term in p of x is nothing but product of roots of p of x. So it's basically saying that the matrix is invertible if and only if determinant is non-zero, which is the same as saying that the characteristic polynomial has a non-zero constant. Yeah, are there any questions?
Can you just, if possible, graded assignment question 3? You don't have to answer, at least the approach.
Okay, I'm not allowed
You
to
know,
solve it.
no. I'm not telling you to solve or give me the
I
answer.
can give you. What is the question, sir? I don't have the question. Can you read it out if you have it?
Yeah.
Yeah.
One second.
Okay. Meanwhile, the others can think about this.
Option
Ma'am,
B.
now screen is much better. Earlier it was very poor, ma'am, in the initial.
No, we should not discuss the answers of the option because it's assignment question.
No. Okay, we will not. Means if A be a 3 by 3 matrix, satisfying.
Somebody is actually told the option that it should be that. So this should not discuss in the.
Okay. No. Okay. Even otherwise, this the question is like this: if A be a 3 by 3 matrix satisfying A cube minus A squared plus A minus I equals 0, then A to the power of 4 equals what? That is the question. So
Can explain any other terms like A5, A6, whatever, or AN.
I'm sorry.
This is actually question somebody is asking you.
Okay. Then maybe let's not get into solving the
okay, never,
assignment.
no, we will not discuss.
Assignment
Yeah.
questions should not be solved.
Okay.
Okay.
We will
So
proceed.
Look at this. So let A be a matrix of order n cross n over a field F. Then rank of A is less than or equal to.
So it should be less than or equal
Is
to
the minimum of M and N.
minimum of m comma n. Minimum of
Minimum of mn.
Exactly.
m
So
comma n.
It is minimum of mn.
yeah. So if you look at again, you can look at any definition of rank that you want to look at, but uh, so in a way, actually, all of because if it's less than minimum of m comma n, it is less than maximum of m comma n, it is less than m and n. But let's say this is the most appropriate answer to select. I mean, each of these quantities are less than the others, right? So in a way, all options are right. But yeah, the most appropriate one to say is minimum of m comma n. So you can look at any of the definitions of rank that you know. So if you want to look at it as, let's say, column rank, which means the dimension of the space.
I have a question. How you said that all the options are correct?
Because if you look at minimum of 2 comma 3, it is less than or equal to maximum of 2 comma 3, right?
Yeah, yeah. Got it, got it.
And definitely it is less than or equal to each of the quantities. So I mean minimum of 2 comma 3 is less than or equal
Got
to.
it, got it, got it. Thank you.
Yeah, so you can whichever definition you look at it, you can get it. So let's say suppose your definition is a column rank, that is number of columns. So the matrix is an m cross n matrix. Um, so the column, if you take the definition as column rank, you know that uh, the vectors are contained in Rn, right? The columns are contained subspace of Rn. Column space is contained in Rn. So definitely the rank has to be less than or equal to m. And how many columns do we have? We have n columns. So again, the dimension of the column space cannot be greater than n. So rank is less than or equal to n. So combining both these, we get that rank is less than or equal to minimum of n.
Ma'am, can you repeat this, ma'am, slowly?
Okay. See, I was just trying to justify why the rank has to be less than or minimum of n comma n using just one definition, saying that it is the number of linearly independent columns or the dimension of the space spanned by columns. Right? If you take this as your definition, whatever we defined as the column rank, so how can you see that the rank of a matrix is less than or equal to m comma n, minimum of m comma n? So, if it is an m cross n matrix, what does this mean? You take a column, it is a vector in Rn, right?
Yes,
Okay.
ma'am.
So, if you take the space generated by all the columns, it is a subspace of Rm. So, the dimension will be less than or equal to m, right? Yeah. I
Yes,
mean,
ma'am.
you
Correct.
Yes,
take,
yes.
yeah. So, next thing is you look at how many columns do we have? We have n columns. So, when you look at the space generated by any n vectors, the dimension will be less than or equal to n. So, in Rm, so you have space generated by some n vectors. So, the dimension of this subspace will be less than or equal to n. Like number of generating vectors is always greater than the dimension. So from there we get rank is less than or equal to n. So combining both of them, you get that it is less than or equal to m comma n. Is this okay? I was just trying to justify it using one of the definitions. Any questions?
We can even tell that row rank and column rank are
Yeah. You can use
Cool.
any of the arguments. You can say that row rank. You can use the definition of row rank, or you can use the the minor definition.
So, madam, here all the options are correct, no? In this case.
Yeah, technically all of them are right.
But I don't understand the first one. Maximum of mn.
Mm-hmm.
How it is correct?
Minimum is less than maximum, right?
Okay, okay.
Yeah. See, they're
no,
just
no. How
asking.
you told? How you told? What you told? Can you please repeat last sentence?
No, all I was
No,
saying is the question is the rank of A is less than or equal to something. So they're just asking for an upper bound for rank of A.
okay. Then less
Yeah.
than or equal.
Yeah. So all of them
But
technically found.
B is equal to. B is equal to.
It need not be equal to. It is still less than or equal to, right? So suppose you take, let's say, A is something like this. So if you compute it, so it is a what? 2 cross 3 matrix. So your M is 2, N is 3. And if you compute the rank, it will be actually 1. So it can be
Okay.
strictly like M and N.
Hmm.
Any more questions? Okay. We are beyond time. Yeah, this is a quick question. So let A be a matrix of order 3 cross 3 and you are given 3 eigenvalues. So what is the trace of A?
Add it.
It is
12.
12.
Yeah, so trace is sum of eigenvalues. So that will be good.
Can take some hard question.
Sorry?
Take some hard question.
Maybe we'll see. Look at it. You can, if you have any questions, we can discuss those also. These are just some sample questions that we have. We'll stop with this unless any of you want to ask something.